understand the Doppler effect, there's a couple of things you need to understand. Firstly, sound travels as a wave. So if we have a sound source, let's say we've got a big air horn here, well, sound travels away from the sound source as a wave. Now, one of the ways we can draw these waves is like this, where we have crests and troughs. In reality, sound waves actually aren't like this. They're actually what we call longitudinal waves, where we have areas that are particles are really close together, and areas where the particles are stretched apart, and then areas where the particles are close together, and it goes on and on and on. But we often draw sound waves like this so we can more easily see the wavelength, that's the distance or the length of a wave, and the frequency, which is the number of waves per second. When we're talking about sound, frequency is like pitch. High frequency sounds are high pitch. What does that mean? That means more waves per second. This is a high frequency wave, whereas this one here is a lower frequency wave. Less waves per second. High frequency is high pitch. Low frequency, low pitch. So let's have a look at what happens with sound from a moving source. So we've got a car moving towards a stationary observer. What happens is the waves are coming away from the car like this towards the observer. But because the car is moving in the direction of the observer, these sound waves tend to stack up on each other. So it looks like we have got a shorter wavelength and a higher frequency. High frequency means high pitch. So when a sound is traveling towards an observer, the waves stack up and the pitch sounds high frequency. When we have a sound source that's moving away from a stationary observer, the waves tend to stretch out. There seems to be a larger distance between the waves, so long wavelength, low frequency. So we've got low frequency, that means low pitch. So a sound travelling away from a stationary observer sounds low pitch. Coming towards a stationary observer, high pitch. It might be helpful to consider an analogy of a boat as it creates waves travelling through the water. In front of the boat, the waves are close together because the waves stack up as the boat moves forward, whereas the waves behind the boat stretch out as the boat is moving away from the waves that it produces. The Doppler effect isn't just related to sound. The Doppler effect applies to all waves, including light. Red light has a longer wavelength and lower frequency than blue light. When a light source is travelling away from an observer, it is said to be red-shifted because the wavelength is longer, so the light appears more red. When light is travelling towards an observer, the light is blue-shifted because the wavelength is shorter. Light from distant galaxies is red-shifted, and this provides evidence that the universe is expanding. Doppler ultrasound is a type of ultrasound used to visualize the movement of blood in vessels within the body. The Doppler effect is used to detect if the blood is flowing towards or away from the ultrasound probe. The Doppler effect is also used to detect if vehicles are speeding by sending radio waves from the speed gun to the vehicle. Speeding vehicles can be detected by a change in frequency of the radio waves returning from the vehicle. And this is a fitting way to finish the video, because the first time I learnt about the Doppler effect was getting caught by a radar gun, driving too fast in a little red Mini when I was 18.